This is a system of nonlinear equations, and that's because at least one of the equations is not a line. One way that we can solve a system of nonlinear equations is by graphing it. And remember, the solution to a system of equations, whether they be linear or nonlinear, is an ordered pair that satisfies both equations. And if we look at their graphs, that would be the intersection point. So let's start by graphing y is equal to the square root of x. This is a graph that should be memorized, one of the ones in our library of functions. We have these 3 points of interest, and essentially it's half of a parabola that opens up and to the right. The second equation actually is a line, and we can write it in slope-intercept form by reversing these terms. So we can see we have a slope of -1 and a y-intercept of 6. So if we come up to the ordered pair 0, 6, and go down 1, right 1, down 1, right 1, it looks like these two graphs are going to intersect at the ordered pair 4, 2. And so the solution to this system of nonlinear equations would be the ordered pair point 4, 2. One way that we can solve this system algebraically is by using the substitution method. So let's see what happens when we algebraically solve this system. The substitution method says to pick one of the equations and solve for one of the variables. So both of these are solved for y. Let's just grab this 6 minus x and plug it in for y in the other equation. So we end up with 6 minus x is equal to the square root of x. And now we've merged both of these criteria into a single equation with one variable. So we can solve this equation for x. It's now a radical equation, and the way that we solve radical equations is by isolating the radical and then squaring both sides. Since our radical is already isolated, we can go ahead and just square both sides. Once we multiply 6 minus x times 6 minus x and FOIL it out, we would get square the first, twice their product, square the second. And on the right-hand side, we end up with the square root of x squared, which is just x. Now we've landed at an equation that is quadratic. And as soon as we notice that we have a quadratic equation, we should set this equal to 0 and then decide which of the methods that we have for solving a quadratic we'd like to use. So we have x squared minus 13x plus 36 is equal to 0, and this does factor. It factors into x minus 9 times x minus 4, and so we end up with x is equal to 9 and x is equal to 4. Now remember, the solution to a system of equations, either linear or nonlinear, is an ordered pair. So we have two x values now that could generate ordered pair solutions to the system. But these ordered pairs should be solutions to both equations, and in order to get the y values, we would simply take the x coordinates and plug them back into the original equation to get the corresponding y values. But remember, we should get the same ordered pair from both equations. So we'll start with y is equal to 6 minus x. Plugging in x is equal to 9, we get y is equal to 6 minus 9, and so we get the y coordinate -3. However, when we plug that into the first equation, y is equal to the square root of x, we end up with y is equal to the square root of 9, and that's equal to +3. So we get two separate y values when plugging in the x value 9, and therefore 9 is not going to generate a solution to the system because it doesn't give us the same ordered pair when we plug it into each of the equations. So now let's check x is equal to 4, and when we plug that into the first equation, we get y is equal to 6 minus 4, so y is equal to 2. So it looks like 4, 2 could be our solution. And when we plug 4 into the other equation, we get y is equal to the square root of 4, which is also +2. So we do get the same ordered pair when we plug it into both of the original equations, and therefore this is the solution to the system. And that matches what we saw when we graphed the system.